All right, so 6.7 is on graphing the basic rational functions. So a rational function is one that involves a fraction, rational meaning fraction, a ratio. So the parent function for a rational is 1 over x. That's the most basic one we have. And from there we can translate it right, left, up, and down. We can make it stretched or compressed, all these different things. So just the parent one, you should definitely be familiar with its shape, that it looks like this. The way we get that is by plugging in some values. So for example, if I asked you to graph y equals 1 over x, right now you would go, well, I don't really know what that shape is. And so then you'd make a t-table and you'd plug in some values, and maybe you'll adjust and be more strategic as you get more comfortable with it and start plotting things and seeing how it works out with your calculations here. But we often do -2 to 2, and you'll see why I do the half there in a moment. But so you do 1 over -2. So when x is -2, it's at -1/2. And then here would be 1 over -1, so that's -1. So at -1, you're at -1. 0, 1 over 0, that's undefined. You cannot divide by 0. So how does that play into this? Well, that means that you can't have anything at an x of 0. So what we often do is put what's called an asymptote, so it can approach it, but it can't actually cross that where x is 0. And then we can try something like 1. So that'd be 1 over 1, which is 1. So 1 would be 1. And 1 over 2, again, a half. So when x is 2, you have a half. But we know we're going to be approaching this, or we will start learning about those asymptotes, that you can approach it. So if we want another point to kind of guide us, we could do something like x being 1/2. So when x is 1/2, we have 1 divided by 1/2. We can multiply by the reciprocal, and we discover the value would be 2. So when x is a half, we're at 2. And so now you have a couple more guiding points. And if you did 3, 4, 5, you get 1/4, 1/5, 1/6, 1/7, 1/8. You can see you're going to get closer and closer and closer to 0, but you can keep getting smaller and smaller fractions. So you can keep getting closer to this line, but without crossing it. So this one has to do with it being undefined, dividing by 0. This one also happens to be an asymptote, but that's just because you can never get a y of 0. There's no x that would make you have a y of 0. So this curve here is centered at the origin. That's why we call it the parent graph. But what that also allows us to do is shift this by shifting that kind of center part, that where the two asymptotes, the vertical asymptote and this horizontal asymptote, are located. We can shift that right, left, up, or down. You can change how stretched or compressed it is by putting a different coefficient in front of your x. We're not going to worry about that so much right now. I'm going to focus on this translation with the HK. You saw that also with the square roots and the cube roots a couple lessons ago. Sorry, you'll see that again in a couple lessons. I recorded this out of order. So HK is like the center of this curve that's in two pieces. So the way you get that is, because it's minus h, the h is always like the opposite of what's showing, and then it's k, so it's what's showing. So in other words, here it's like plus 0, so it's 0 and then 2 for the center, or where the asymptotes cross is at the point x0, y2, 0, 2 right here. And so I could make my asymptotes through there. And just like before, if I had made my x 0, I would have it undefined because I'd be dividing by 0. So what we're going to do a lot of is looking at the denominator and seeing when is it 0, when is it undefined. And that creates these asymptotes, the separation between the two curves. And then the y we're adding 2 to the y, because it's this plus 2. So that's why the y values are all shifted up 2. Here, it will end up being the opposite, and then keep it the same. This is the minus, and then there's the h, and then plus, and then the k. So there's the h and there's the k. So it always ends up being the opposite of what's showing. So it shows -5, which means +5, and then 3. So 3. Opposite and then same. So at 5, 3 is where our asymptotes intersect. And you can also see this if I were to plug in 5, again, it would be undefined. So using the idea of the restrictions, the excluded values, I can determine my vertical asymptote, and that can help when you have like multiple choice and you're trying to see what it is, or if you're trying to figure out where the curve is centered at. That's a good way of saying, okay, well, I should center my table at 5. So then I should do some numbers below it and above it. And perhaps, 4 is not good because of some, reason, or 3, and you can adjust from there. So for the rest of the curve, there's a couple things that you can do to get more points. One, make a t-table. For example, this would be 1 over 3 minus 5 plus 3. So that would be 1 over -2 plus 3. 3 and minus a half would be 2 and 1/2. So at 3, I'd be at 1, 2 and a half. I could plug in 4. That'd be 1 over -1 plus 3, which is -1. -1 plus 3, so that'd be 2. So at 4 for the x, we have a y of 2. And what you might notice is that this is kind of similar to the shape right here. So the shortcut really is when you go over 1 from the center, you're doing the reciprocal. So the reciprocal of 1 is 1. The reciprocal of 2 is a half. The reciprocal of 3 would have been a third, a fourth, a fifth, etc. The reciprocal of a half is 2. The reciprocal of a quarter would be 4, etc. So it's the reciprocal function when it's 1 over. Not if it's 2 or anything else, but when it's 1 over, then it's a reciprocal. And so that's why that pattern works. So these are both 1 over, so I can just go from my center. Reciprocal of 1 is 1. Reciprocal of 2 is a half. Reciprocal of 3 is a third, etc. Reciprocal of a half, so halfway, half a unit, would be 2. Reciprocal of a third would be 3, for example, etc. But I can just get closer to that curve. Don't cross it, just get closer to it. Closer to your asymptote, and make this curve get closer to that asymptote. And then similarly, the reciprocal of -1 is -1. The reciprocal of -2 is -1/2. The reciprocal of -1/2 is -2. So I just get a couple guiding points. And you can see the same pattern. 2 would be a half. 1, -1, half would be 2. 1's reciprocal is 1. Reciprocal of 2, and I'm going from the center. 1, 2 is a half. The reciprocal of a half would be 2. And use those to guide my curve. The other option, and you'll do more of this when you're in a pre-calc class, is again thinking about the center, thinking about the horizontal and vertical asymptotes. You'll learn how to do those more algebraically as well for other cases besides this standard HK format. And then you can also graph x-intercepts and y-intercepts. So here, if I were to solve for the x-intercept, that's when y is 0. So I'd have 0 equals 1 over x plus 2. I would subtract 2 from both sides. I would then multiply both sides by x, or I can cross multiply. -2 equals x equals 1. Divide by -2, and I would have an x-intercept of negative 1/2 when y was 0. So the point would be negative 1/2, 0, which we can see in this graph. Negative 1/2, 0 was the x-intercept. If we try to find the y-intercept, we would be setting the x equal to 0, and we can't have it undefined, and that's why we have the asymptote. On number 2, if we were to do this and we solved, we would get some value where when we approximated it, it would be right around there. And if we found the y-intercept, it would be close to 3, but again, just shy of 3. So same shape, negative 3, opposite same. Just want to review this HK because it's going to come up quite a bit throughout this course with graphing opposite, and then this is like plus 0, so 4, 0 is the center of that one. This one would be negative 1, negative 2, and this one would be 0, 0 because it's plus 0, plus 0. This one has a 3 here, and so it'll behave a little bit differently. You might try like, okay, I know it can't be 0 down there. That would be the asymptote. Just like here, I know it can't go through negative 1. And then if I plug in 3 divided by 1, well, that's easy enough to calculate. 3 divided by 1 is 3. And if I did 2, I'd have 3 divided by 2, which is 1.5. You could do that not too difficultly, approximate it on your graph like that. 3 would be another nice strategic one because 3 divided by 3 goes in nicely into 1. Another one that might be kind of nice to do when you're dividing, but when you have 3 divided by something, might be like 6, because then you have a half. And you might be seeing that it is kind of petering out at this line right here, and that's because of that other asymptote. Remember, the asymptotes were centered at 0, 0, or intersected at 0, 0. And we could also put in like negative 1, then that would be negative 3. We could have put in negative 3, and that would be then negative 1. We could put in negative 6, and that would be negative 1/2. So it's slightly different than the parent, because the parent would have been 1, 1 to a half. A half would have been 2. This would have been the parent. So you can see that it's been stretched vertically. It's 3 times as high. So instead of 1, it's 3. Instead of a half, it's 1.5. It's 3 times as high, etc. So this just multiplies the y values by 3. It scales it up. It stretches it. I do want to show a few other things as far as the not actual graphing, but maybe comparing graphs. I'm going to project this. Here we go. Here is 6.7 for the XYZ assignment. You can evaluate. That's kind of like making a t-table. We're plugging in 0 for the x and finding the y that goes with it. Plugging in negative 4 for the x. Plugging in negative 2. Plugging in 6. Plugging in 2. And when you plug in 2 here, you'll end up with 2 minus 2. And so the idea here is that it, in this case, is undefined. So you can hit D and E. Next question. Here it asks you for domain. That's a fancy way of saying what can't the input be? The x's be, right? The input. And x cannot be negative 5 because that would make it undefined. So you're basically, when it says x can't be, you're stating the restrictions or the undefined, the value where it would be undefined, the excluded values. Next one. Again, same thing. It's all about the denominator. You might notice there's a difference of squares. So it's x plus 6, x minus 6. and this is x plus 6, so the x plus 6 is cancel, but it's at any point you can't divide by 0. So this still would create a restriction. So the domain is any x can go in here. That's domain, or what x's can go in here. Anything except for negative 6, because that would make the denominator 0, and you can't divide by 0. All right, so then here, what makes this denominator 0? Well, this is a difference of squares, so it's x plus 5 times x minus 5. So what would make that work is the zero product property. Let me see about using the other pen, this pen. Okay, so this is x plus 5 times x minus 5. And we want to know, when is it 0? When would it be undefined? So if this is 0, 0 times anything is 0. And if we have something times 0, then we get 0. So what makes this 0? So you can either say x plus 5 equals 0 and solve, subtracting 5 from both sides. 0 minus 5 is negative 5. Or you might be able to even think about it and just say to yourself, well, what minus 5 is 0? And determine that x being 5 would make that 0. And so here you'd have 10 times 0 is 0. So it is the solution. Here you would have 0 times negative 10. That's still 0. So both of those are solutions to this equation, to the question about when would you be dividing by 0? What should be excluded? What would make it undefined? All right. And then number 5. This one's matching. And so what can be very helpful is thinking about that HK. Where is it centered at? Where are the asymptotes? So it would be at -2. This is minus a negative, so the opposite is what you always go for. -2. Oops, that's really aligned. -2, comma 0 as where the asymptotes go through. So let's go to -2, 0. There and there is where it should be, so that's not it because it goes through it. Let's scroll down. -2, 0. So the only one that works is this one because it's going here and here as the asymptotes. At -2, 0 is the center, and there's that lovely curve we've just been talking about. Alternatively, pick some points and see if they work. So for example, if you plug in, I have to go back to the equation. If you plug in -1, does it give you 1, or does it give you -1/2, or does it give you -1/2, or does it give you -1/2? So a lot of these might match up, and so you're just trying to find the one that works in all cases. So you might have to do a couple test points. But this is the one, if I can get this to line up again, I can't, that will make it work. There we go. -1 should be 1 when you plug it in. So -1. 1 over -1 plus 2 would be 1 over 1, which is 1. So when your x is -1, you have a y of 1. When x is -1, you have a y of 1. When x is -1, you have a y of 1. You didn't have that here, or here, or here. And I just picked -1 because we were already down here looking at this example, but I could have picked any x coordinate, and I just did one that was nice value to calculate. So like this would have been a nice one to also check at -3. Or you could check this one at +2 or 0. All right, 2 more to kind of discuss briefly here. Okay, so here again, it's all about the denominator. So we would have a vertical asymptote for this one would be going through -3, this one +4, this one 1, this one -2. So this one has an asymptote at 1, so that's why we want this one, because that would have an asymptote. It's undefined when x is 1. We can't have the curve go through it. This one looks like it's centered right around the 4, so that would match up with this b, -4 being the expression x minus 4, because 4 would make that undefined. This one, it looks like -2, so it's this +2, because -2 would make it undefined. And lastly, this says -3, so where its asymptote is, so that means it has to be -3, making it undefined, so A. Last but not least, this is function notation relating to rationals, and this will come up more in future courses, in particular calculus, but we can still do it with our knowledge of function notation. Let's do our best here. So here, f of x right here is 9x, because that's what f of x equals. So you'd have 9x minus f of a. Well, f of a means instead of having an x right here, oops, right, it doesn't like that. Instead of having an x right here, we have an a. So instead of having an x, we're having an a. So it'll be 9a. So we're going to subtract 9a. If it was a quantity, you'd need to make sure to put it in parentheses and subtract both or all things. Divided by x minus a. Well, we can factor out a 9. And then these factors cancel. They go in one time. And so our answer is just 9. The next one, I'm going to erase, and we can try that one. The input is x plus h. So instead of having an x, we're going to have x plus h. So we're going to have 9 times x plus h minus f of x. And so again, f of x is literally this 9x. F of x equals 9x. And then divide that by h. So if we distribute the 9 here, we can then combine like terms. So we have 9x plus 9. I can't see what I'm doing when I'm this close. Let me try to make that a little bit cleaner. 9h minus 9x all over h. These cancel out, 9x minus 9x, so we have 9h over h. The h's cancel out, so we're just left with 9. So it's the same answer for that as well. And this is 2 different ways. This is really y that goes with an x, and the y that goes with the a value. So it's really rise over run slope. This is slope in a function notation manner, and this is, when you get into calculus, is the slope as well, but h represents you getting closer and closer to the tangent line, a slope at an instantaneous point. So these are both slope formulas, and it's function notation, and eventually you'll be using it again in calculus and pre-calc. All right, so that is 6.7. Essentially, what you need to get out of this is think about what makes the denominator 0. Where are your restrictions? And that is a vertical asymptote.